6, I think it's time zone 3, paper 2. It's reviewed later on, but I thought I'd do the whole thing. It's a good question on buffers and weak acids and whatnot. So HNO2 weak acid, and therefore it will break down partially to give H plus and NO2 minus. You're told lots of information, so you're told you've got a 1.0 mol per litre solution. You're going to need that information later on. And you've been asked to state the formulas of the conjugate acid and conjugate bases in there. Now this is an acid dissolved in water, so you've got the acid itself, the HNO2, nitrous acids, and its conjugate base. Now to work out the conjugate base of something, simply remove H plus. So you go from neutral to minus and you've lost an H. But you've got to remember that water also can behave as an acid. It can also release H plus. Its Kw or Ka is very, very different to the acid, so it doesn't release very much of it, but if it behaves as an acid, this is it acting as an acid, and if you release H plus, you're left with hydroxide. Then it's a pretty standard kind of buffer calculation where you're given lots of information, including the 1.0 mol per litre, mol per decimeter cubed, and you're asked to work out the concentration of the conjugate base. Now you always start off by writing an equation for Ka. Now always Ka is used to work out any pH calculations or any weak acid calculations. Now remember, in a weak acid the concentrations of these are the same as each other, or can be assumed to be, but in a buffer they're not. We were told in the question the concentration of the HNO2, so we know that one. We're told in the question the pKa of nitrous acid is 3.25. So you can work out its Ka by doing 10 to the minus 3.25, which is 5.62 times 10 to the minus 4. So we know that value there. We're also told in the question we've got a pH of the buffer, which is 3, and so, or 3.00, so we can say for definite then that the hydrogen ion concentration is 10 to the minus 3, which is 3 times 10 to the minus 3, which is here. So we know that. Rearrange it all, you end up with the concentration of NO2 minus or A minus. I could have put there NO2 minus. Plug all those numbers in once you've rearranged this equation. I'm not going to do that for you. Gives you that times that over that, and that's the answer. Next question is a fairly standard oxidation number question. If you remember always that each oxygen can be assumed to be -2, except in those exceptional cases that you've learnt. Likewise, hydrogen is always +1, except when an element or with a metal. And so if we know the hydrogen is +1 and each oxygen is -2, it must be, to add up to 0 here, because this is a neutral compound, the nitrogen must be +3. Please write +3 minus rather than 3 plus. 3 plus would be the charge, and that would be wrong. That would be, we're told by the IB to give that as incorrect. That's the charge, not the oxidation number. So over the page then, you've been asked to work out some stuff about some chemicals you've never heard of: picric acid, carbolic acid, or you've heard of aspirin. Hang on, computer glitch, one sec. And so you've been asked to suggest how modern chemists improve communication when naming chemical compounds. Now you have to know that the International Union of Pure and Applied Chemistry meet regularly to agree a system of naming chemicals. So they come up with sort of what they call systematic naming of chemicals, and that would get any mention of IUPAC or systematic naming gets a mark. And the whole point there is these are names based on the structure. And we can get computers to do that for us now. You plug a very complex structure into a computer and it can give you the proper IUPAC name. Remember, by the way, if you're asked to give the IUPAC name of a compound, like, for example, this is a different question now, but just something like MnO2, you'll be asked to give the IUPAC name. It would be manganese And then you have to give the oxidation number of the manganese here, which is 4 in Roman numerals, oxide. So if ever you're asked to give an IUPAC name for a compound, particularly transition metal compounds like this, watch out, make sure you've got the oxidation number in there somewhere. Anyway, you've been told in here there's an ester functional group, and the ester functional group is here. I'm sure you can recognise that. Two other functional groups, we've got a carboxyl here. You're not allowed to say carboxylic acid. We call it a carboxyl as the functional group, carboxyl functional group. The homologous series would be a carboxylic acid. And we've got a phenyl ring. That's this ring here. You can't say a benzene ring, that's not allowed, or even anything as vague as an aromatic ring. You can't call it benzene because benzene is a specific substance, which is that. Right, so you can't call it a benzene ring. So you have to know those and practice those functional group names. Practice that, please. Ethylothanoate. Deduce the structure and name for a functional group isomer of ethylothanoate. I'm just going to draw ethylothanoate to start with, so that you can sort of see how we turn this condensed structural formula into a displayed structure. So we've got a CH3 at the end, then a carbon, then off that there's 2 oxygens, followed by a carbon. So that's how we know it's an ester here. And then we've got a CH2 and a CH3. I'm only showing you that for interest really, or as an aside. And you have to come up with any valid isomer, as long as it's got 4 carbons, 8 hydrogens and 2 oxygens, that's not also an ester. So a good example of that would be something like the one that's in the mark scheme, which would be butanoic acid. Like that would be nice. Okay, so butanoic acid. 1, 2, 3, 4. Okay. The catalyst is used in the manufacture of this ester, so we should know that catalysts increase the rate of reaction. That's a mark, and they do that by providing an alternative pathway with a lower activation energy. I'll drop the words here, but I'm being lazy, so I'm just going to write EA. And you're then told you can make ethylothanoate from the reaction of ethanol with ethanoic acid. Fine, sure, we should know that anyway. Both reactants can be synthesized from ethane through a series of reactions. It's not something you probably do in reality, but it suggests here that you can do that by turning the ethane into chloroethane. And the first step is given. We all know that we can write that out. We're very good at this now, aren't we, as a group? Like so, to give you those, but the condition you need there, of course, is UV light. You're then asked to draw the mechanism of chloroethane being converted to ethanol. And again, we know these mechanisms really well. Now, chloroethane, of course, is a primary halogenoalkane. It's going to react, therefore, via a single step, one step SN2 mechanism. So we should be really comfortable with the idea that primary halogenoalkanes always react via SN2. And so we've got the hydroxide here, and we show the attack of the delta plus carbon, which is this one. You don't actually need the delta plus and the delta minus for the mark. I'm going to draw them on out of habit, really, and that's what I've taught you. That helps you to remember that the negative lone pair attacks that carbon. Please have it going to the carbon, not a plus or the delta plus directly, but to the carbon. And then in that same first step, so concerted all at the same time mechanism, you've got an arrow there, and you get one mark for this arrow, and you get 1 mark for this arrow in the mark scheme. But remember here, although it's a one-step mechanism, we should know that this forms what we call a transition state. So at the same time as the carbon-oxygen bond is forming, the carbon-chlorine bond is breaking. So if you're drawing this, make sure that you show a dotted line between the oxygen and the carbon. Please don't put the O and then the H. And we have the carbon-chlorine bond breaking. That whole thing is minus charge. We're just going to hang off this carbon, whatever's hanging. This is this carbon here, isn't it? So we've got 2 hydrogens on there and a CH3. You can draw that any which way around you like. It's showing the 3D nature of that in the mark scheme. But there's no indication that the 3D sort of shape of that is required, nor do you need to have it as 180 degrees, although that is normal. But you need to show the negative charge and you need to show the partial bonds as drawn. And then you draw the products, which are of course the ethanol and the chloride ion that's kind of fallen off. Alright? You need both of those for the final mark. And then you've got to work out what the high resolution NMR looks like for ethanol. I've done lots of this. I'm just going to draw ethanol again, or in fact I'll just refer to it up here. So the number of signals, got a signal for the first CH3, signal for the CH2, and a signal for the H. They're all in different chemical environments. I'm just going to, for the sake of clarity, I'm going to label them A and B and C, but we get a mark for saying there's 3 signals there. What's the chemical shift range for each one? The first one, A, is just next to a CH2. If you look that up in the data book, you'll see that's 0.9 to 1.0. Make sure your dots are really clear. Make sure you know the units are ppm, although it doesn't specify you need a mark there. B, this is next to an OH, and if you look that up, it should be clear enough that it's 3.3 to 3.7 ppm. And then C, the OH itself, they can come almost anywhere in an NMR spectrum, but usually between 1.0 and 6.0 according to the data book. All right. The integration traces, now for A there are 3 hydrogens, B there's 2 hydrogens, and C there's 1. So you get a mark for saying 3 to 2 to 1, 3 and 2 and 1. And what splitting pattern would you get here? Now it's pretty generous in the mark scheme here, quite rightly. A would be a triplet, that's straightforward. It's the adjacent carbon. This carbon is the adjacent carbon, you can't see it. It's got 2 hydrogens on it. 2 plus 1 is 3. And so for A, we'd get a triplet. For B, it's a complex answer, this one really, because this, well, there's more than one way of answering this, but I've taught you just to worry about the hydrogens on carbon, so that's what we're going to do here. And so the hydrogens on carbon are, there's 3 of them on the adjacent carbon, so 3 plus 1 is 4, and you get a mark for quartet. That's absolutely fine, that's what I've taught you, that will work nicely. In reality, it might also couple to the hydrogen, although that's kind of complicated. And so you will get away also with multiplet there for the answer. And then the OH, the way that I've taught you to deal with OHs is put broad singlet. In reality, you would get a mark for saying it might couple to the hydrogens on the adjacent carbon, so you get a mark for triplet as well. The IB are quite generous when it comes to all of this stuff, because it's kind of complicated in real life. Here, we've got question D, the overall reaction of converting ethane to ethyl ethanoate using its elements is set out there. You've been asked to calculate the enthalpy change for this reaction using information on page 12 or section 12 of the data booklet. Right, so you didn't have to watch me write all this out longhand, I've just done it. But when you're doing a bond energy calculation, make sure please you set out the grid as you've been taught. Obviously this one's quite a big one, so try and get it into the box for the exam, and if you don't quite, make a note clearly in the box that some of the answer is fallen outside the box. But just show all of the energy required to break the bond, so that's a positive enthalpy change because you're breaking the bonds, that's endothermic. And all the bonds formed in the product, and you can see here when I was working through, I actually drew or at least drew one of the products to make sure I had everything. I even slipped up a little bit along the way. Look, there's 2 carbon-carbon single bonds in there, one there and one there. Tick them all off as you go, but top them up, get a mark for getting that right, tick, a mark for getting that right, and then a mark for doing the endothermic ones, and these are exothermic, so you take them away. So it's take away that lot, and you end up with 663 there at the enthalpy change. Now the next question says, one student used bond enthalpy data correctly and calculated the enthalpy change for the reaction below to be 0 kilojoules per mole. Another student used enthalpy change of formation data and got a value of -4. How can you get different values? Well, for a start, there's only one mark here, so any one of these will do. But bond enthalpies are not bond enthalpies are average values. So I'm not going to write the whole thing out. You can do that yourself. Average values of bond enthalpies are not specific to the reaction. Bond enthalpies only apply to gaseous molecules, and that's not the case when you've got liquids involved. So that means it's only an approximation. That's really the answer I'd give. It does have in the mark scheme the second set of data was specific to the actual reaction. Next thing is to calculate the enthalpy change of formation of ethyl ethanoate. Use section 1 and section 13 of the data booklet and the value of -4. Right. So if we look, we first of all work out what the enthalpy change of formation is for that reaction. What is that reaction actually? So it's when 4 lots of carbon, so this is the formation of a compound from its elements. So 4 lots of carbon, 4 lots of H2 in the standard states, remember, and 1 oxygen molecule come together to give C4H8O2. That's a liquid, right? So that is what the reaction is that we're interested in, and we should know from the data. Well, we should know it, but we might look it up from the data book. The enthalpy change for a reaction is equal to the sum of the enthalpy changes or formation of the products, take away the sum of the enthalpy changes of formation the reactants. Now, how do we tackle this question though? To answer this question, we've got to use the reaction above, which is not the same as the enthalpy change of formation of the reaction. The enthalpy change of that reaction is given as -4 kilojoules per mole. So that's that value there, -4. And then what we need to do is to look up the enthalpy changes of formation of water. If you turn to the section 13 of the data book, water comes to 286. This is the one we've been asked to work out. The enthalpy change of formation of ethanoic acid in your data book is -484, and the enthalpy change of formation of ethanol in your data book is -278. So the enthalpy change of formation of the products, the sum of them, is the one you're interested in, delta H of formation of the ester, that's the thing we're trying to look up, we're trying to work out, sorry, plus -286 minus, we're now on this side, sum of the enthalpy change of formation of the reactants. Now, just note here that this is a 1-to-1 to 1-to-1 ratio, so we have to multiply anything up here, which is nice. But we've got -278 for ethanol and -484 for the ethanoic acid. And if you rearrange this now, you've got -4. You'll end up adding 286 and adding -278 and -484, if you see what I mean. You rearrange this equation properly, and I'm not going to do that for you. That should come to 8 kilojoules per mole. That's that question. calculate the standard entropy change now using the data booklet. Now it would generally, just realised I've written down the wrong answer here. It's minus 480. Sorry about that, minus 480. I was looking at the answer for the next one. The standard entropy change calculation, you can use the same data book and a value is given to you there. So delta S for a reaction is exactly the same as before, but it's the sum of the total entropies, or the sum of the standard entropies of the products. Take away the sum of the standard entropies of the reactants, plug the numbers in. I'm going to hurry on a little bit now, but this one does come to 8. Now remember, this is in joules per Kelvin per mole, so slightly different, and that's important for when you're working out delta G, which is what you've got to do next. Delta G is equal to delta H minus T delta S. You've been given a value for the delta H of reaction is minus 4 kilojoules per mole. We've been told this is under standard conditions, so it's 298 Kelvin. We've got to convert, for 1 mark, we're going to convert that to kilojoules per Kelvin per mole, which is 0.008. And if you pop that into the calculator, you get minus 6.4 kilojoules per mole. 2 marks for that one. 1 mark for that, 1 mark for that. This reaction is a negative delta G, so it is spontaneous. But because this value, delta S, is a positive value, if you increase the temperature, the overall value for delta G becomes more negative if you increase the temperature. And so there's an increase in spontaneity, it becomes even more likely to be even more spontaneous. The next one, you've got a graph of how the rates change. Now, if the forward reaction is going to start very fast, as always, forward reactions start very quickly and will tend to tail off, become slower as the reaction proceeds, as reactants are used up, depending on the rate equation, of course, what that would look like. But because it's an equilibrium, at the start there's no products at all, there's no reverse reaction, but as time progresses the rate would increase. But the definition of dynamic equilibrium is when the rate of the forward and reverse reaction are the same, so they're going to end up in the same rate as each other. And you've got to label these forward and reverse reaction, and you've got to then determine the delta. You've been asked to work out what the equilibrium constant for this is, and you need the equation delta G equals minus RT natural log of K. So we've got to rearrange that equation to make natural log of K the subject. Delta G of RT. Well, we've worked out delta G already, but we've got to have this in joules per mole because we're using the gas constant here, and that's in joules per mole per Kelvin, right? So we need to have all of this right, and we need to convert 60 degrees also to Kelvin. So we plug in the number for delta G that we worked out. Which was minus 6,400 if it's converted to joules, divided by R times the temperature, which is 333 Kelvin. And that will give us a value of 2.313, the first part, and then we've just got to do the inverse operation. So we've got to do e to the minus that, and that gives us a value of K of 10.10, 10.9. Goodness me, this goes on. I might just stop it there. I don't know. If you want help with the rest of it, give me a shout.